Let's look at example 7. This comes from 7.3. And it says a plane is flying with an airspeed of 170 miles per hour and a heading of 52.5 degrees. Its true course, however, is at 64.1 degrees from due north. If the wind currents are a constant 40 miles per hour, what are the possibilities for the ground speed of the plane? So, in order to do this question, we need to understand the wordings that they're using in here. So we want to make sure that we look up what it means to be a heading, what it means to have a true course, what it means to be due north, and what the ground speed means. All of those items that I've underlined were found in the 7.2 guided notes. So if you go back to the 7.2 guided notes and you look under the navigation, you're going to see all those definitions that we're talking about here. So let's review that, and then let's take a look at what it says. It says for the solution, represent the velocity of the plane and the velocity of the wind with vectors. And then the resultant, remember from the definition, the resultant vector will be the ground speed and true course of the plane. So this is going to tell us what to do. First, measure the angle from due north, the 52.5 degrees, and you're going to measure it clockwise. And then you draw a vector in that direction with a magnitude of 170 to represent the heading and airspeed. And then you're going to draw a second vector from an angle of 64.1 degrees from due north. Because the second vector must be the resultant, the wind velocity will be some vector originating at the top of the first and ending at the tip of the second, and having a length of 40.0. So that is drawn for us right here. So we have this figure that is drawn for us. We have from due north 64.1 degrees and from due north 52.5. So if we find the difference between the two, that will give us that little portion. So let's write that in. So I'm going to subtract, I'm going to take 64.1 and I'm going to subtract 52.5 degrees, and that will result in the angle theta here, which would be 11.6 degrees. And it says here first, so let me write what I wrote. Theta is equal to 64.1 minus 52.5, which gives me 11.6 degrees. First, use the law of sines to find the angle alpha. So here's alpha. This angle right here is what we're looking for. And so the law of sines says this. The sine of the angle divided by the side across from it, or 170, will be equal to the sine. We just found that one to be 11.6 degrees to the side across from that. And so now we're going to, what I would do here is I would multiply both sides by 170 so that I can get the sine of alpha. And so I'm going to put this in my calculator, and I end up with the sine of alpha is equal to 0.8546. Alpha, to find alpha, do the inverse sine. So you take the inverse sine of 0.8546 and we'll come up with the value of alpha. And it also says because alpha is positive in quadrants 1 and 4, we will have two values that are possible. So when we take this on the calculator returns 58.7 degrees. I think I said quadrants 1 and 4. I'm at quadrants 1 and 2. So this is the one that gives us 0.8546. But there's also whatever angle has a reference angle of 58.7 degrees here. So we're looking for the angle that opens up like this. And we can find that, I'll call it alpha prime, by using the reference angle formula. 180 minus 58.7 means that alpha prime would be 121.3 degrees. So we see there are two different triangles that can be formed with the three vectors. And in this figure, we see both of them. So we either have this right here, this triangle, or we have this triangle with this obtuse angle. So because there are two values for alpha, then there would be two values for beta. So for beta, you would take the 180, because all three angles have to equal 180, and you would subtract the other two angles. Putting this in my calculator, I get beta is equal to 109.7 degrees. So in this triangle here, this is 109.7 degrees. For this triangle, where this alpha is obtuse, I'll call it now beta prime, and I'll say, okay, well that would be 180 minus 11.6 degrees, and subtract 121.3 degrees from that, and that will give us our alternate, which this, if we're using this triangle, it would be 47.1 degrees. And now we're missing this this red, the resultant vector, because the question had said to find the ground speed, and that resultant vector is the ground speed. So using the law of sines, now I'll write the law of sines like this because I'm looking for the side. So now I can set this up. I want to use the angle that is across. So the 11.6 and the 40. And then I'm looking for x, and I'll use the angle across from that, which we found to be 109.7 degrees. Now, could we use the 70 and 58.7? Yes, we could. So the sine of the angle across from the 40 is 11.6 degrees. Solving this means that I'm going to multiply both sides by the sine of 109.7 degrees to isolate the x. So here I ended up, put this on my calculator, I got 187 miles per hour. Here, I'm going to now do a similar setup for this one. And I'm going to call it, I'm just going to call it alpha prime, or I'm sorry, x prime, to distinguish between the two. So the angle that is across from x prime is 97.1. And so now I would multiply both sides by the sine of 97.1 so that it would get rid of it out of the denominator here. And then put this in your calculator, and you should end up with 146 miles per hour. So those are my two answers. And the reason why I wrote 187 and 146 is because I was sticking with the 3 significant digits. And so let's fill in the blank here. So there's a possibility that ground speed for the planes are 187 miles per hour and 146 miles per hour. And that's how you would do this type of question. So this is an application example using the ambiguous case and vectors.